Now in this lecture we will find out the radius of the circle using two different methods. In the drawing we have a circle. The center of this circle is at this point O. Line segment AB equals to 6 units. Line segment AD equals to 18 units. Line segment BC equals to 13 units. This angle BAD equals to 90 degrees. This angle ABC equals to 90 degrees. Our mission is to find out the radius of this circle. So first of all, we do a construction from point C and draw perpendicular on AD. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction, we created here quadrilateral ABEC. This quadrilateral ABEC has 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth angle must be equal to 90 degrees. So, quadrilateral ABEC, this quadrilateral has 4 right angles, therefore quadrilateral ABEC is a rectangle. And you know that the opposite sides of a rectangle are equal to each other, that is to say side EB equals to side EC. But AB equals to 6 units according to what is given as the equation. Therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. BC equals to AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. And what is the length of line segment ED? From the drawing it is very easy to see that ED equals to AD minus AE. AD minus AE. AD equals to 18 units. AD equals to 18 units. AE equals to 13 units. AD minus AE is 18 minus 14, that is 5. So ED equals to 5 units. In the next step, we will join points D and C together by a straight line. By joining points D and C, we created the right triangle DEC. In the next step, we will implement the Pythagoras theorem in the right green small triangle EDC. Here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle DC is DC, therefore the square of the hypotenuse is DC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC squared plus ED squared. So DC squared equals to EC squared is equals to 6. Therefore, EC squared equals to 6 squared, that is 36. plus ED square. ED equals to 5 units, therefore ED square equals to 5 squared, that is 25. So in conclusion, we found out that DC squared, the square of the hypotenuse of the green triangle, equals to 36 plus 25 is 61. Here we'll take a root out of this equation, and we get that DC, this is the hypotenuse of the green triangle, equals to the square root of 61 units. We can write in the drawing that the hypotenuse DC equals to the square root of 61 units. In the next step, we join points E and D together by a straight line. By joining points B and D, we created the right triangle ABD. In the right triangle ABD, we implement the Pythagoras theorem. By PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD, this right triangle ABD is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus AD squared. In conclusion, we found out that according to the Pythagoras theorem, in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared equals to AB squared. AB equals to 6, so AB squared is 6 squared, that is 36, plus AD squared. AD equals to 18 units, therefore AD squared is 18 squared, that is 324. So in conclusion, we found out that BD squared equals to 36 plus 324. So BD squared equals to 36 plus 324 is 360. Here we will substitute 360 by 36 times 10. So here BD squared equals to 36 times 10. Here we'll take a root out of this equation and we'll get that BD equals to the square root of 36 times 10. So here we'll take a root. We'll take 36 out of the root. The square root of 36 is 6. So we get that BD, that is the hypotenuse of the right triangle ABD, equals to the square root of 36, that is 6, times in the root we have only 10. So it is 6 times square root of 10 units. So here the hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. Okay. In the next step we'll find out the area of triangle BDC. We find out the area of the green triangle, triangle BDC. The area of any triangle, and especially of the green triangle, triangle BDC, here the squared bracket is the sign for the area. It means the area of triangle BDC. It is equal to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of the green triangle, triangle BDC, will be equal to the base of the triangle. We'll choose the base as BC. Times the height over 2. In order to find out the height to the base, we'll extend side BC by a straight line, and from point D we will draw perpendicular to the extended BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the extended side BC and the perpendicular from point D as F. So actually by doing this construction we get the quadrilateral ABDF. Quadrilateral ABDF, again quadrilateral ABDF as 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. This angle equals to 90 degrees, and therefore quadrilateral ABDF, that has 4 right angles, we relate to it as a rectangle. So I write it down. Quadrilateral ABDF is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DF. And I know that AB equals to DF. But it is also given us in the question that AB equals to 6 units. So we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. DF equals to 6 units. But what is actually line segment DF? DF is the height to the extended base BC. Therefore, DF is the height, and it is equal to 6 units. Why DF is the height? Because of the fact that DF creates 90 degrees with the extended base BC. Okay, now we can easily find out the area of the green triangle, triangle BDC. The area of the green triangle, triangle BDC, it is equal to the base of the triangle. We choose the base is BC, and BC equals to 13 units according to what is given as the question, times the height. The height of the base is equal to 6 units over 2. So the area of triangle BDC is equal to 6 over 2 is 3, and 3 times 13 is 39. The area of the green triangle BDC equals to 39 square units. So in the next step I will present to you a new rule, and we will implement the new rule in our drawing. Okay. This will be actually rule number 1. According to rule number 1, if a triangle ABC is blocked, you can use the word blocked or inscribed by a circle. So we actually have a circle point O is the center of the circle, and inside this circle we have triangle ABC that is blocked or inscribed by this circle. This is triangle ABC. Triangle ABC is blocked by this circle. Actually, a triangle is blocked by a circle only and only if all the 3 vertices of the triangle are touching the circle. Exactly like in this drawing. Here, this vertex of triangle ABC touches the circle at point A, this vertex of triangle ABC touches the circle at point B, and finally this vertex of triangle ABC touches the circle at point C. So all the 3 vertices must touch the circle at different points in order that a triangle will be blocked by a circle, like in this drawing. So if a triangle ABC is blocked or inscribed by a circle, we will define the radius of this circle. That is to say, OM equals to capital R, according to our definition. The length of side AB is A units, side AC equals to C units in its length, and side BC equals to B units in its length. So we actually can find out the radius of this circle that blocks triangle ABC only by knowing the side lengths of the triangle ABC that is blocked by this circle. So the radius of this circle, that is to say capital R, then will be equal to the multiplication of the side lengths of the triangle by each other, that is A times B times C, over 4 times the area of triangle ABC. Okay, So whenever you have a triangle that is blocked by a circle, you can find out the radius of the circle that blocks triangle ABC by only by knowing the side lengths of the triangle that is blocked by the circle. Okay? So we actually can implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC that is blocked by this circle. Why triangle BDC is blocked by this circle? Because of the fact that this vertex of triangle ABC touches the circle at point B. This vertex touches the circle at point C, and finally this vertex of triangle ABC touches the circle at point D. Therefore, we can definitely say that the green triangle ABC is blocked by this circle. I write it down. The green triangle BDC is blocked by the circle, and therefore we can implement rule number 1 in our drawing. And we get that if we define the radius of this circle as capital R, here OM is the radius of this circle that is equal to capital R according to our definition, then the value of the radius capital R will be equal to the multiplication of the side lengths of the green triangle by each other. That is to say, it is BC times CD times DB over 4 times the area of the green triangle DBC. Okay. So the radius of this circle that blocks the green triangle BDC will be equal to BC is 14 units, CD is square root of 61 units, and here BD is 6 times square root of 10 units. Over 4 times the area of the green triangle BDC, and we already found out that the area of the green triangle BDC it is equal to 39 square units. So that's actually the answer to the question. Well, because according to the question we have to find out the radius of this circle, that is capital R, and capital R equals to this expression. In the next step, we will just simplify this expression by dividing both the numerator and the denominator of this expression by 13. And we get that capital R, the radius of the circle, equals to 13 over 13 is 1, so 13 will get cancelled. So in the numerator, we left only with square root of 61 times square root of 10 times 6. Over, we have to divide the denominator also by 13, so it is 4 times 39 over 13 is 3, so it is 4 times 3. So if we found out that the radius of this circle capital R, it is equal to the square root of 61 times the square root of 10 times 6 over 4 times 3. 4 times 3 is 12. Here we will divide both the numerator and the denominator of this expression by 6, and we get that the radius of this circle, capital R, equals to the square root of 61 times the square root of 10, and 6 over 6 is 1, so 6 will get cancelled, over 12 over 6 is 2. So the radius of this circle equals to the square root of 61 times the square root of 10 over 2. Here we'll use the algebraic identity that states that the square root of A times the square root of B equals to the square root of A times B. According to this algebraic identity, we get that the square root of 61 times the square root of 10 equals to the square root of 61 times 10, all divided by 2. So the radius of this circle, capital R, equals to either the square root of 61 times 10 is 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finish with the first method. In the next step, I will present to you the second method to find out the radius of this circle. In the second method, in the first step, we will do the things that we have already done in the first method. So we do it quickly. From the point C, we draw perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. So here, we're doing this construction, we create a quadrilateral ABEC. Inside quadrilateral ABEC, we have 1, 2, 3 right angles. The sum of 3 right angles is 470 degrees. So here, the fourth angle, I will not repeat on the same thing that we have already done in the first method. Here, the fourth angle must be equal to 90 degrees. And therefore, quadrilateral ABC that has 4 right angles, we will relate to it as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6 units according to what is given as the equation. Therefore, EC must be also equal to 6 units. Likewise, according to the same rule, that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE, but BC equals to 13 units, therefore AE must be also equal to 13 units. What is the length of line segment ED? From the drawing it is very easy to see that ED equals to AD minus AE. AD is 18 units, AE is 13 units, therefore 18 minus 13 is 5. So we found out that ED equals to 5 units. So until now we did all the things that we have already done in the first method. From now on we will continue with the second method. In the second method, from point O, that is the center of this circle, we'll draw perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as capital N, and we define the touching point of the perpendicular from point O and AD as M. In the next step, I present to you a new rule, and we will implement the new rule in our drawing. Okay? According to the new rule, it will be actually rule number 2. A perpendicular from the center of a circle to any chord bisect the chord. So according to rule number 2, whenever you have a perpendicular from the center of the circle towards any chord, it will bisect the chord. So we draw the drawing of this sentence, rule number 2. We have this circle could be any circle. The center of the circle is at this point that we define as point O. And here we have chord BC. That could be any chord. And from the center of this circle, that is to say from point O, we will draw perpendicular to chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from the center of the circle, that is to say from point O to chord BC as M. According to this rule number 2, the perpendicular from the center of the circle to chord BC, that is to say OM, bisect chord BC. That is to say BM equals to MC. BM equals to MC according to this rule number 2. So whenever you have a perpendicular from the center of the circle towards any chord, it will bisect the chord. So we actually can implement this new rule number 2 in our drawing. Why? Because in our drawing we have perpendicular ON from the center of the circle, that is to say from point O to chord BC. And therefore, according to rule number 2, the perpendicular ON bisects chord BC. That is to say BN equals to NC. So I write it down. In our original drawing, we have perpendicular ON to chord BC. And perpendicular ON is of course from the center of the circle, that is to say from point O to chord BC. According to rule number 2, the perpendicular ON to chord BC bisects chord BC. If perpendicular ON bisects chord BC, it means that BN equals to NC. BN equals to NC according to rule number 2. Repeat again. Perpendicular ON from the center of this circle towards chord BC bisects chord BC. That is to say BN equals to NC. Okay. In the next step, we will focus on quadrilateral ABMN. In quadrilateral ABMN, the upper quadrilateral, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, and quadrilateral ABMN that has 4 right angles, we will relate to it as a rectangle. So I write it down, quadrilateral ABMN is a rectangle. Quadrilateral ABMN is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AM equals to BN. So side BN. AM equals to BN. Likewise, we relate to the lower quadrilateral MNEC. Here, in the lower quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. So quadrilateral MNEC that has 4 right angles, we will relate to it as a rectangle. So I write it down. Quadrilateral MNEC is a rectangle because it has 4 right angles. Okay, but we also know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. So we actually can summarize what we did until now. First of all, we found out that according to rule number 2, BN equals to NC. BN equals to NC. And according to the rule that the opposite sides of a rectangle are equal to each other, we found out that BN equals to AM. So we can write here that BN equals to AM. Likewise, according to the same rule, we found out that NC equals to ME. So we can write here that NC equals to ME. And from this logical equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. That is to say, side AM equals to side ME. Okay. In the next step, we will extend line segment DA until it touches the circle, and we will define the touching point of the extended line segment DA at the circle as F. By doing this construction, we can do code FT. Okay. We actually draw perpendicular ON to code BC. ON is a perpendicular, it is absolutely a straight line. Any perpendicular must be a straight line. And we have rule number 1 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. Likewise, according to the symbol, if you focus on the lower side of the straight line ON at point M, here the sum of the angles must also be equal to 180 degrees according to rule number 1. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. So therefore, this missing angle must be equal to 90 degrees. So we actually found out that this angle equals to 90 degrees and this angle equals to 90 degrees. That is to say, line segment OM is perpendicular to chord FD. Again, line segment OM is perpendicular to chord FD. Okay. So I write it down. We found out that line segment OM is perpendicular to chord FD. And line segment OM exists from the center of this circle, that is to say from point O. And whenever you have a perpendicular from the center of a circle to any chord, it will bisect the chord according to rule number 2. If chord AM bisects chord FD, it means that FM equals to MD. Okay, FM equals to MD. FM equals to MD according to rule number 2. Here FM, it is very easy to see that FM equals to FA plus AM. FA plus AM equals to FM. So I write it down. FM equals to FA plus AM. And it is equal to MD. Here, MD equals to ME plus ED again. ME plus ED equals to MD. ME plus ED. So in conclusion, we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. line segment AM equals to line segment ME. It's because of the fact that the two line segments are equal to each other, we can cancel them out. And we're left only with FA equals to ED. FA equals to ED. This line segment FA equals to line segment ED. But we have already found out that ED equals to 5 units. So we can write here that ED equals to 5 units. And from this equation, FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. Here we can write down that FA equals to 5 units. In the next step, we will extend side BA by a straight line until it touches the circle at point P. So here we have chord FD that intersects with chord PB at point A. And according to the old rule number 2, whenever you have two chords that intersect with each other, this is to say, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement the old rule number 2 in our drawing. Why? Because in our drawing, we have chord FD that intersects with chord PB at point A. Again, chord FD intersects with chord PB at point A. So I write it down. In our original drawing, we have chord FD that intersects with chord PB at point A. Therefore, we can implement here the old rule number 2. And according to the old rule number 2, we will get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. So I write it down. FA times AD equals to PA times AB. This is according to the old rule number 2. And then FA times AD equals to PA times AB. According to the old rule number 2. FA equals to 5 units, AD equals to 18 units. PA is the missing line segment, so we will leave it as it is. And finally, AB equals to 6 units, so we substitute AB by 6. So in conclusion, we found out that according to the old rule number 2, 5 times 18 equals to PA times 6. Here we will divide this expression by 6, and we get that PA, the missing line segment, equals to 5 times 18 over 6. So PA equals to 18 over 6 is 3, and 3 times 5 is 15. So we found out that PA, the line segment that we are looking for, is equal to, the missing line segment equals to 15 units. PA equals to 15 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. It will be actually rule number 4. Actually, rule number 4 states that whenever you have two chords that are perpendicular to each other, you actually can find out the radius of the circle that contains the chord according to a special formula. So I write it down. First of all, we'll draw the drawing of the rule number 4. So this circle could be any circle. The center of this circle is at this point E. And we have here chord AB. This is chord AB. That is actually perpendicular to chord CD. It's perpendicular to this chord called CD. That is to say, they create between them at the intersection points 90 degrees. Therefore, they are perpendicular to each other. We will define the intersection point between the two chords as O. So you can see here that chord AB is perpendicular to chord CD at point O. So if chord AB is perpendicular to chord CD and they are perpendicular to each other at the intersection point O. Point O. Then the following equation will be true. By using the following equation, we can find out the radius of this circle that contains the two chords that are perpendicular to each other. We define the radius of this circle. Here EM equals to capital R. According to our definition. So, whenever you have two chords that are perpendicular to each other, the following equation will be true. 4 times capital R square, again capital R is the radius of this circle, will be equal to AO square plus OB square plus CO square plus OD square. So if two chords are perpendicular to each other, then according to this rule number 4, we get that 4R square, R is the radius of this circle, will be equal to AO square plus OB square plus CO square plus OD square. Okay? We can actually implement rule number 4 in our drawing. Why? Because In our drawing, we have also two chords that are perpendicular to each other. Here, chord FD is perpendicular to chord PB at point A. At point A, the grade between them 90 degrees, therefore they are perpendicular to each other, and for that reason, we can implement here rule number 4. So I write it down. In our original drawing, we have chord FD that is perpendicular to chord PB, and they are perpendicular to each other at point A. And for that reason, we have here two chords that are perpendicular to each other. Whenever you have two chords that are perpendicular to each other, you can implement rule number 4. Okay, therefore we can implement here rule number 4. And according to rule number 4, first of all, we'll define the radius of this circle OM is the radius of this circle as capital R. So, because of the fact that we have here two chords that are perpendicular to each other, we can implement here rule number 4. And according to rule number 4, 4R square, R is the radius of this circle OM, it is equal to capital R, equals to FA square plus AD square plus BA square plus AB square. Again, 4R square, R is the radius of the circle, equals to FA square plus AD square plus BA square plus AB square. So I write it down. R square, again R is the radius of the circle, equals to FA square plus AD square plus PA square plus AB square, according to rule number 4. Okay. The only missing variable here is R, is the radius of the circle, and that is exactly the radius that we are looking for. So by solving this equation, we find out the radius of this circle, that is capital R. So 4R square equals to FA square. FA equals to 5, therefore FA square equals to 5 square, that is 25, plus AD square. AD equals to 18 units, therefore AD square equals to 18 square, that is 324, plus PA square. PA equals to 15, therefore PA square equals to 15 square, that is 225, plus AB square. AB equals to 6 units, therefore AB square equals to 6 square, that is 36. So in conclusion, we found out that according to rule number 4, 4R square equals to 25 plus 225 is 250, and 324 plus 36 is 360. In conclusion, we found out that 4R square equals to 250 plus 360. 250 plus 360 is 610. So 4R square equals to 610. Here we divide this equation by 4, and we get that R square equals to 610 over 4. Here we will take a root out of this equation, and we will get that capital R equals to the square root of 610 over 4. That is to say, capital R, the radius of the circle that we are looking for, equals to the square root of 610, and the square root of 4 is 2. So the radius of this circle, capital R, the radius that we are looking for, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first method, of course. In the drawing, we have a circle. The center of the circle is at this point O. Line segment AB equals to 6 units. Line segment BC equals to 13 units. Line segment AD equals to 18 units in length. This angle BAD equals to 90 degrees, and this angle ABC equals to 90 degrees. Also, our mission is to find out the radius of this circle that we defined as OM, that is equal to capital R. We want to find out the value of capital R. So first of all, we did the construction, that is to say, from point C we draw perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction, created a quadrilateral ABCE. This quadrilateral ABCE is 1, 2, 3 right angles, and therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that quadrilateral ABCE has 4 right angles, we will relate to quadrilateral ABCE as a rectangle. But we know also that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But BC equals to 13 units. Therefore, AE must be also equal to 13 units. And what is the length of this line segment ED? The length of line segment ED, it is very easy to see from the drawing that it is equal to AD minus AE. AD is 18, AE is 13. AD minus AE is 18 minus 14, that is 5. So line segment ED equals to 5 units in its length. In the next step, we join point C and D together by a straight line. By joining point C and D, we created the right triangle ECD. Right small great triangle ECD. In the next step, we implemented the Pythagoras theorem on the right small great triangle is ECD or EDC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right small triangle EDC is DC, therefore the square of the hypotenuse is DC square. It must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to EC square plus ED square. So in conclusion, according to the Pythagoras theorem, we found out that in the right great triangle EDC, DC square equals to EC square plus ED square. So DC square equals to EC square. EC equals to 6, therefore EC square is 6 square, that is 36, plus ED square. ED is 5, therefore ED square is 5 square, that is 25. In conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61. So DC square equals to 61. We took a root out of this equation and we found out that DC equals to the square root of 61 units. Here the hypotenuse DC of the right triangle EDC equals to the square root of 61 units. In the next step, we joined points B and D together by a straight line. By joining points B and D, we created this right triangle, triangle ABD. Then we implemented the Pythagoras theorem on the right triangle ABD. Okay, the hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD square. BD square. And according to the Pythagoras theorem, it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB square plus AD square. Here, BD square equals to AB square plus AD square. So BD square, that is the square of the hypotenuse, equals to AB square. AB equals to 6, therefore AB square equals to 6 square, that is 36. Plus AD square. AD equals to 18 units according to what is given as the question, therefore AB square is 18 square, that is 324. In conclusion, we found out that BD square equals to 36 plus 324. 36 plus 324 is 360. So we found out that DB square equals to 360. Then we substituted 360 by 36 times 10. Here BD square equals to 36 times 10. Then we took a root out of this equation and we found out that BD equals to the square root of 36 times 10. Then we took 36 out of the root. The square root of 36 is 6. So we found out that BD equals to 6. Inside the root we left only with 10. So BD, the hypotenuse BD equals to 6 times square root of 10 units. Here the hypotenuse BD, this hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. In the next step, we calculated the area of this green right triangle, triangle BDC. Here the area, the square bracket is the sign of the area. For the area, it means the area of triangle BDC. The area of any triangle, and especially the area of triangle BDC, equals to the base of the triangle times the height of the base over 2. I must emphasize that the height to the base must create 90 degrees with the base. Okay, so the area of triangle BDC equals to the base times the height over 2. We choose the base of the green triangle BDC as BC. So here the base equals to BC times the height over 2. In the next step we will find out the height of the right triangle BDC, of the green triangle BDC. It is not right triangle. We extended side BC by a straight line, and from point D we draw perpendicular on the extended BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So here DF creates 90 degrees with the extended BC, therefore DF is the height to the base BC of the green triangle, triangle BDC. So when we will find out the value of DF, it will be the height to the base BC. Okay? So by doing this construction, we created a quadrilateral ABDF. This quadrilateral ABDF has 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. And therefore, quadrilateral ABDF that has 4 right angles we relate to it as a rectangle. Quadrilateral ABDF is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So first of all, here, quadrilateral ABDF is a rectangle, and according to the rule that the opposite sides of a rectangle are equal to each other, we will get that AB equals to DF. AB equals to DF, but it is given us the equation that AB equals to 6 units, if AB equals to 6, and from this equation 6 equals to AB equals to DF, we will conclude that DF is also equals to 6 units. Okay? DF equals to 6 units, that is to say the height to the base equals to 6 units. Now we can easily find out the area of the green triangle BDC. The area of the green triangle BDC equals to the base. The base is BC, and BC equals to 13 units, so we substitute the base BC by 13 times the height. We just right now found out that the height to the base is 6, all divided by 2. So the area of the green triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of the green triangle BDC, the area of this green triangle BDC equals to 39 square units. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, if a triangle ABC is blocked by a circle, this triangle ABC could be any triangle, and it is blocked by this circle. What is a triangle that is blocked by a circle? A triangle is blocked by a circle only and only if all the three vertices of the triangle are touching the circle. Exactly like in this drawing. This vertex touches the circle at point A. This vertex touches the circle at point B. And this vertex touches the circle at point C. Therefore, we can definitely say that this triangle ABC is blocked by this circle. So whenever you have a triangle that is blocked by a circle, like in this drawing, we define the radius of this circle OM as capital R, then you can find out the radius of the circle that blocks the triangle only by knowing the side lengths of the triangle. So you can find out the radius of this circle capital R. It is equal, here, the length of side AB is A units, the length of side AC is C units, and the length of side BC is B units. So the radius of this circle equals to A times B times C, that is the multiplication of the side lengths of the triangle by each other, over 4 times the area of triangle ABC. So if we know all the 3 sides of a triangle that is blocked by a circle, you can easily find out the radius of this circle that blocks the triangle. Why? Because you can find out the area of the triangle only by knowing the 3 sides, the length of the 3 sides of the triangle. And in this way, we actually find out the radius of the circle that blocks the triangle. Okay, now we can implement this rule number 1 in our drawing. Why? Because in our drawing we have this great triangle BDC. Vertex B touches the circle at point. This vertex touches the circle at point B. This vertex of the triangle BDC touches the circle at point C, and this vertex touches the circle at point D. Okay. Therefore, we can definitely say that the great triangle BDC is blocked by this circle, and for that reason we can implement here rule number 1. So I'll repeat again. The great triangle BDC is blocked by this circle, and for that reason we can implement here rule number 1. According to rule number 1, here we define the radius of this circle as capital R, or M equals to capital R. Capital R equals to the multiplication of the side lengths of the green triangle by each other. This is BC times CD times BD. BC times CD times DB over 4 times the area of the green triangle BDC. The area of this green triangle BDC. BC equals to 13 units, CD equals to the square root of 61 units, and BD equals to 6 times square root of 10 units. Okay, and there, it is over 4 times the area of the green triangle DBC. And we've already found out that the area of the green triangle BDC equals to 39 square units. And this expression, it is actually the answer to our question. We have to find out the radius of this circle, capital R. And capital R equals to this expression. So this is the answer to our question. In the next step, we just simplify this expression by dividing both the numerator and the denominator of this expression by 13. 13 over 13 is 1, so in the numerator we left only with square root of 61 times square root of 10 times 6 over, we have to divide also the denominator by 13. So it is 4 times 39 over 13 is 3. So in the denominator we have 4 times 3, that is 12. In conclusion, we found out that the radius of this circle, capital R, equals to the square root of 16 times square root of 10 times 6 over 12. Here we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so 6 will get cancelled. And we left only with square root of 61 times square root of 10 in the numerator. Over 12 over 6 is 2. Okay. So the radius of the circle equals to the square root of 61 times 10 over 2. We use the algebraic identity that the square root of A times square root of B equals to the square root of A times B. In order to find out the value of the square root of 61, times the value of the square root of 61 times the square root of 10 equals to the square root of 61 times 10 according to this algebraic identity, all divided by 2. And 61 times 10 is 610 over 2. So we found out that the radius of this circle, capital R, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the first question. In the next step, I actually explained how to find out the radius of the circle according to the second method. In the second method, in the first step, we used all the things that we already found out in the first method, or we did all the things that we did in the first method. So I'll repeat on it quickly. From point C we draw perpendicular on AD. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point C and AD as E. By doing this construction, we created a quadrangle ABEC. In quadrangle ABEC, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, quadrangle ABEC is 4 right angles, therefore quadrangle ABEC is a rectangle. Quadrangle ABEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6, therefore EC must be also equal to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, AE equals to BC. But BC equals to 13 units, therefore AE must be also equal to 13 units. What is the value of line segment ED? ED equals to AE, ED equals to AD minus AE. That is 18 minus 13, that is 5. Okay, so we did all the things until now in the first method, and from now on we did the things according to the second method. We continued with the second method, that is to say, from point O, that is the center of this circle, we draw perpendicular on chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and called BC as capital N, and we define the touching point of the perpendicular from point O and AD is capital M. Then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, a perpendicular from the center of the circle to any chord bisect the chord. So we have here this circle, the center of this circle is this point, point O, and we have here chord BC, that could be any chord, and from the center of the circle we have perpendicular OM to chord BC. And according to this rule, rule number 2, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. So whenever you have a perpendicular from the center of the circle towards any chord, it will bisect the chord. Like here, we have perpendicular OM from the center of the circle towards chord BC, and therefore it will bisect chord BC. That is to say, BC equals to MC. BM equals to MC. Again, BM equals to MC. Okay, according to this rule, rule number 2. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have perpendicular ON from the center of the circle, that is to say from point O towards chord BC, and therefore, according to rule number 2, it will bisect chord BC. That is to say, BN equals to NC. I repeat again, we have perpendicular ON from the center of the circle towards chord BC, and therefore it will bisect chord BC according to rule number 2. That is to say, BN equals to NC. If perpendicular ON bisects chord BC, it means that BN equals to NC, according to rule number 2. Then we focus on quadrilateral AB, MN. In this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral ABMN that has 4 right angles will relate to it as a rectangle. Again, quadrilateral ABMN is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Then we related to quadrilateral MNEC. Inside quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. Therefore, quadrilateral MNEC that has 4 right angles, we will relate to it as a rectangle. Quadrilateral MNEC is a rectangle. Here, quadrilateral MNEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize what we did until now. According to rule number 2, we found out that BN equals to NC. And according to the rule that the opposite sides of a rectangle are equal to each other, we found out that BN equals to MA. So we can write here that BN equals to MA. And according to the same rule that the opposite sides of a rectangle are equal to each other, we found out that NC equals to ME. So we can write here that NC equals to ME. And from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. Again, AM equals to ME. Here, side AM equals to side ME. Okay, then we extended line segment EA until it touches the circle at point F. By doing this construction, we created a chord FD. And we took perpendicular ON to chord BC a couple of minutes ago, and because of the fact that ON is perpendicular to BC, to chord BC, ON is a perpendicular, it is absolutely a straight line. And we have the old rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to the old rule number 1. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle, this angle, the missing angle must be also equal to 90 degrees. Likewise, according to, we actually focus on the lower side of the straight line ON at point M. Here, the sum of the angles must be also equal to 180 degrees according to the old rule number 1. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to the old rule number 1. Therefore this missing angle must be equal to 90 degrees. So we actually found out that this angle equals to 90 degrees and this angle equals to 90 degrees. So therefore OM is perpendicular to FD. Okay, OM is perpendicular to FD. So here OM is perpendicular to chord FD, and whenever you have from the center of the circle, that is to say from point O perpendicular to any chord, it will bisect the chord. Perpendicular OM from the center of this circle bisect chord FD. If perpendicular OM bisects chord FD, it means that FM equals to MD, according to rule number 2. Okay? So Fm equals to Md according to rule number 2. What is the value of Fm? Fm equals to Fa plus Am. Okay, Fm equals to Fa plus Am. So you can substitute Fm by Fa plus Am. And what is the, so it is equal to Md. And what is the value of Md? MD equals to ME plus ED. Again, MD equals to ME plus ED. So we can substitute MD by ME plus ED. In conclusion, we found out that FA plus AM equals to ME plus ED. Okay? But we have already found out that AM equals to ME. Yeah. Those two chords are equal to each other. AM equals to ME, therefore we can cancel them out. Okay, so we cancel them and we left only with FA equals to ED. So we actually found out that FA equals to FA, this chord FA equals to this chord ED. But we've already found out that ED equals to 5 units. So we can write here that ED equals to 5 units, and from this equation FA equals to ED equals to 5, we will derive that FA equals also to 5 units. Here, line segment FA equals to 5 units. In the next step, we extended side BA by a straight line until it touches the circle at point P. So we have here chord PB, that intersects with chord FD at point A. And according to the old rule number 2, whenever you have two chords that intersect with each other, like in this drawing, we have chord AB that intersects with chord CD at point O, we can implement here the old rule number 2, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay. So here we have chord FD that intersects with chord PB at point A. Chord FD intersects with chord PB at point A. Therefore, according to the old rule number 2, we'll get that FA times AD equals to BA times AB. Again, FA times AD equals to BA times AP. Okay. According to the old rule number 2, FA times AD equals to PA times AB. Okay, according to old rule number 2, FA equals to 5 units, AD equals to 18 units, PA is the missing 9 segments, so we leave it as it is, and AB equals to 6 units, so we substitute AB by 6. In conclusion, we found out that FA times AD equals to PA times AB. 5 times 18 equals to PA times 6. Okay? Then we divided this equation by 6 and found out that PA equals to 5 times 18 over 6. 18 over 6 is 3 and 3 times 5 is 15. So we found out that the missing chord called PA equals to 15 units in its length. Okay? Then I presented to you rule number 4 and we implemented rule number 4 in our drawing. According to rule number 4, if we have two chords that are perpendicular to each other, we actually can find out the radius of the circle that contains the chord according to a special formula. And here we have chord AB that is perpendicular to chord CD at point O. Why they are perpendicular to each other? Because of the fact that they create 90 degrees here at the intersection points. Therefore they are perpendicular to each other. So whenever you have two chords that are perpendicular to each other, like in this drawing, a certain formula will be true. If we define the radius of this circle EM as capital R, then the following formula will be true, that 4R square, R is the radius of this circle, equals to AO square plus OB square plus CO square plus OD square. So 4R square, R is the radius of the circle, equals to AO square plus OB square plus CO square plus OD square. Okay, so whenever you have two chords that are perpendicular to each other, you can implement this rule number 4. By implementing rule number 4, we can find out the radius of this circle that contains the two chords that are perpendicular to each other. Okay, we actually can implement rule number 4 in our drawing. Why? Because in our drawing we have two chords that are perpendicular to each other. That is to say, chord FD is perpendicular to chord PB at point A. That is to say, at point A, they create between them 90 degrees. Therefore, they are perpendicular to each other, and therefore we can implement here rule number 4. I repeat again. In our original drawing, we have chord FD that is perpendicular to chord PB at point A. Point A is the intersection point, and they are perpendicular to each other at point A, that is the intersection point between the two chords. And because of the fact that in our original drawing we have two chords that are perpendicular to each other, we can implement here rule number 4. And according to rule number 4, if we define the radius of this circle as capital R, that is to say OM equals to capital R according to our definition, then 4R squared will be equal to FA squared plus AD squared plus PA squared plus AB squared. Again, 4R squared, R is the radius of the circle, equals to FA squared plus AD squared plus PA squared plus AB squared. Repeat again, 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared, according to rule number 4. Okay, so here FA equals to 5, therefore FA squared equals to 25. AD equals to 18 units, therefore AD squared equals to 18 squared, this is 324. PA equals to 15 units, therefore PA squared equals to 15 squared, this is 225. Plus AB squared, AB equals to 6 units, therefore AB squared is 6 squared, that is 36. So in conclusion, we found out that 4R squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. So 4R squared equals to 250 plus 360. So 4R squared equals to 250 plus 360 is 610. 4R squared equals to 610. We divided this equation by 4, and we found out that R squared equals to 610 over 4. Here we took a root out of this equation and found out that r, the radius of this circle, the radius that we are looking for, r or capital R, equals to the square root of 610 over 4. That is to say, r equals to the square root of 610 and the square root of 4 is 2. So in conclusion, we found out that the radius of this circle, capital R or M, that is equal to capital R, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.